Our previous video discussed how to graph polynomial equations of degree 2, quadratic equations. This video will discuss graphs of higher order degree polynomials, degree n polynomials. We'll start by outlining the basic shapes you can see when you graph such objects. So there's a couple of cases here. The first I will consider is when the coefficient in the highest degree term, an, is positive, and additionally, if n is even. So in this situation, the graph of a polynomial could look something like this. There are a few things I want to point out. If n is even, then the function comes down, wiggles a bunch of times, and then goes up again. Think about a parabola. That's when n is equal to 2. A parabola comes down and then up. A polynomial equation is similar, except there could be more wiggles down here before it goes up again. There are, at most, n zeros in a degree n polynomial. So there can be at most n places where the graph intersects the x-axis. Furthermore, there can be n minus 1 turning points. So a place where a function goes from decreasing to increasing or from increasing to decreasing. So there can be at most n minus 1 turns. So this is the situation when you have a positive first coefficient and n even. If an is negative and n even, it's a similar picture, but just reflected about the line, the x-axis. So I'm going to just quickly draw a similar picture, but when the first leading coefficient is negative, it's the same idea, except it starts from way down here and ends going back down in the same direction. Similarly, of course, you could have at most n zeros and n minus 1 turns because it's the same picture just flipped upside down. Now what happens if an is positive and n is odd? In this situation, it's very similar to the even case, except for one small difference. In this case, the function starts down here and comes up, turning a few times before heading up to larger and larger numbers towards infinity in this direction. Again, you can have at most n zeros and at most n minus 1 turns where it transitions from going up to going down or vice versa. And if you notice, I say at most n zeros. That's because I could take this whole picture, add a big constant to it, and push the diagram up so that there are no zeros. It does not intersect the x-axis at all. This is similar to the situation when you're graphing a parabola and the parabola is above the x-axis. However, if n is odd, since I start coming in from negative infinity down here and turning and then go towards positive infinity on the right side, you'll notice that I at least have to have 1 0 minimum. So there is a minimum of 1 0 in the case when n is odd. And the case when the leading coefficient is negative and n is odd is the same picture, just flipped upside down. So I'll draw a situation that you might see. There's a situation where n could be odd. Let's see a few concrete examples. How about this example? What if I did f of x is equal to x minus 1 times x minus 2 times x minus 3. This is a polynomial of this form. Maybe in this case I'll write it in expanded form so you can identify easily the coefficients. This, I believe, would be x to the third minus 6x squared plus 11x minus 6. So this is indeed an odd case. I have an odd polynomial. You could see that also because I have 3 terms here, and if I multiplied everything out, you can quickly see that x times x times x would give you an x cubed. And the leading term is positive. I'm going to graph this over here. So the picture looks like this case here. Just plotting a point or two to get an indication of what's happening, I could plug in x equals 0. That's one of my favorite numbers to plug in, 0, because the calculation is simple. I get negative 6. So I'm here at negative 6 when x is equal to 0. And I can also quickly identify the zeros. That's why I wrote it in this form. You can see that if I plug in 1 or 2 or 3, I get an output of 0. So I have zeros at 1, 2, and 3. So I know the basic shape. I have a point here. I know where the zeros are. I can plot more points if necessary, but I believe the picture is going to look something like this. Just based on the information that I have here. If I ever wanted to know a little bit closer refinement of what the graph looks like, of course you could plot more points. Let's compare that to what I would get if I changed the function a little bit. How would it be different if I had x minus 1 squared times x minus 2, x minus 3? So the only thing I did here was I changed the first term to be a squared instead of a power 1. The zeros are still in the same place, but now I have a different case of the basic shape. I have 2 x's from this term, 1 from this, and 1 from this. So I'm in the situation where an is positive and n is even. So this is my new picture. Let me just briefly sketch that. In this case, if I plug in x equals 0, I get positive 6. The zeros are still at the location 1, 2, and 3. So the function is going to come down. The first 0 is at 1, but notice what happens. In the previous situation, if I plugged in a number a little bit smaller than 1, like if I plugged in 0.9 or something, I would get a negative result here. If I plugged in a positive number, like if I plugged in 1.1, a little bit to the right of 1, I'd get a positive number. So it's negative on this side, positive on this side. However, in the second example, it doesn't matter if you're a little bit smaller or a little bit bigger than 1. This term will always be positive because I'm squaring a term. That means the function comes right down like this and then just touches barely the x-axis before coming up again. X minus 2 is a degree 1 term, so it's going to change sign, go like this. X equals 3 is a degree 1 term. So there is a good sketch of my picture. So what I guess I'm trying to say is, if you have a squared term or a term where I have an even power here, that's going to affect the graph by just touching the x-axis up here before bouncing down again. Maybe as a more extreme example, I could do the graph of x minus 1 squared times x minus 2 squared. What would that look like? So that would be, here, let me do it over here. Here's x equals 1. Here's x equals 2. If I plug in 0, I get positive 2. I notice that I have another degree 4 polynomial where the first coefficient is positive. So this is my basic shape. But in this case, I'm squaring both zeros, meaning both times I'm just going to barely touch the x-axis at that location before going up again. So the picture might look like this. So it touches, it comes up, it goes down again, and just touches at 2 because that's a squared term before going up again. So there's a basic idea of what the graph might look like. Okay, let's finish this video with one more example of graphing with these ideas. What if I had the function f of x is 1 minus x to the 4th? Now this I will factor. This is a difference of squares. It's 1 squared. Actually, maybe I should be more clear about the squares. 1 squared minus x squared squared. So I see it's a difference of squares. And a difference of squares can be easily factored into 1 plus x squared times 1 minus x squared. I have a new difference of squares in the second term. So this is 1 plus x squared times 1 plus x times 1 minus x. So in this example, I was able to use the difference of squares trick to factor. However, be careful. You can't expect to factor polynomials quickly. In fact, factoring polynomials is a very difficult problem for large degree n. So in this class, and actually in any future class, you're generally never going to be expected to factor very large polynomials. Sometimes in special cases such as this one, however, it's relatively easy. So I have zeros. If I have x equals negative 1 or x equals positive 1, then I get a 0. So I get zeros at plus or minus 1. I'll draw the graph over here. So there's minus 1 and there's plus 1. If I plug in x equals 0, I get 1, so I'm up here. I have a degree 4 polynomial, but negative. So I'm in this case over here. I only have 2 zeros. 2 of them are kind of imaginary from this term. So you could plot more points, you could see what's going on, but I know the graph's basic shape is like this, comes up to 1. Let's kind of sketch what I have here. That's supposed to be at 1. This is similar to the graph of a parabola, except it's a little bit wider near this peak. Okay, so there was a very brief introduction into graphing polynomial equations. Wonderful.